Hello, everyone, and welcome to Math 8, Lesson 5. This is going to be on Chapter 7, Section 3, which starts on page 262. And this chapter, or this section, is technically on approximating square roots, okay? But as you'll see, I've put in parentheses here, classifying numbers, because this is kind of the secondary title of this section. And this is actually the first thing we're going to be doing, and the first thing we're going to be focusing on in this section is classifying numbers due to or based on what type of number they are. Okay, and as far as the types of numbers, that's what we're going to be talking about first. And then the first example is actually going through and classifying numbers. So even though it's not in the title of the section, it's actually in the book. I felt like it needed to be mentioned here because, like I said, the first example and the first good bit of notes are going to be based on, like I said, classifying numbers. So talking about what types of numbers there are. Okay. So to get us started here, we are going to start with, some basic definitions of different types of numbers here. And then we'll go into more of a sense of how we can tell what types of numbers these are. Okay. So what we're going to have here, these are the definitions. So let me go ahead and write that out here. And the first definition we're going to talk about is what the definition of rational number is. Or rational numbers. Okay. So first thing I want you to notice is with the word rational, okay, the first 5 letters of the word rational are RATIO, which spells the word ratio, okay? And that's actually going to give us a little hint as to what rational numbers actually are. So if we see that the word rational starts with the word ratio, okay, we're going to say that rational numbers are numbers that can be written as a ratio. Now, some people have been a little confused about what written as a ratio, what a ratio actually is. Okay, now these two things aren't necessarily the same. Okay, and we can talk about why they're different in a different at a different time. Okay, but what you can think of it in terms of what we're going to be getting into here, you can kind of think of a ratio as a fraction. Okay, when you see the word ratio here in these definitions, it's okay if you think of them as just fractions. Okay, so ratio, rational numbers, numbers that can be written as a ratio. Okay, or like I said, if you want to think of it as a fraction. Now, the next type of number that we've got to talk about is what we call irrational numbers. Okay. Now, before we even get into the actual definition, let's take a look at this word irrational. Okay. So the word irrational, if you know anything from English class in terms of prefixes of words, okay, the prefix of the word irrational is IR, ear. So in this case, we've got the term irrational. So just so everybody's on the same page, the prefix ear in a word means not. So if somebody's irresponsible, that means they are not responsible. If somebody's being, I guess in terms of a people sense, if somebody's being irrational, they're not being rational. What's the same thing here? Irrational literally means not rational, okay? So irrational numbers are the opposite of what rational numbers are. So irrational numbers are going to be numbers that cannot be written as a ratio. Once again, if you want to think of it as a fraction. These are numbers that can't be written as fractions, okay? So that's the difference between rational numbers and irrational numbers. Now, on the next page, we'll actually talk about how we can tell if a number is rational versus irrational and how we, know the difference there, okay? And then the last definition or last term we need to talk about is what the real numbers are. In the definition, we're going to give real numbers, and you might think, well, why do we call them real numbers? Well, there are mathematical reasons, okay? And just to not confuse anybody, real numbers are just going to be the numbers that we see in this class, okay? So basically every number you're going to see in this class is going to be a real number. You won't have to worry about anything other than real numbers until you get to all the way to Algebra 2, okay? So in this case, when we're talking about real numbers, basically we're talking about any number we're talking about, but more specifically, we're talking about all rational and irrational numbers. So basically, if the number is either rational or irrational, it is a real number, okay? And once again, that's every single number you're going to see this year. So all the numbers you've seen so far as scientific notation, square roots, okay? Anything written with an exponent, you can write that's going to be a real number, okay? So all the rational and irrational numbers together, that makes up what we call the real numbers, okay? Now you're going to see here towards the middle of the notes, well, actually towards the end, we'll talk about what a Venn diagram. So we have a Venn diagram that makes this distinction so you can tell how real numbers, irrational numbers, and rational numbers, how they all behave with one another, okay? And if you know what a Venn diagram is and can understand how the Venn diagram works, it should go a long way in telling you how all these sets of numbers react with one another, okay? But let's go ahead and go on. So that's the, actual textbook definitions of all these different words. But now let's go ahead and see how we're going to identify. So in this case, this section is going to be how to identify numbers. Okay? And what I mean by that is, well, how are we going to know what a real number is? Okay? Well, a real number, okay, is so let me put it this way. Real numbers are any number you will see in this class. So once again, anything that we've seen. So 5 is a real number, okay? So let me shrink this down a little bit, give us a little more space. Oop. So 5 is a real number. 3.2 times 10 to the negative 7 is a real number. 6 to the third power is a real number. The square root of 26 is a real number. The negative square root of 49 is a real number. And once again, you can just keep going on. So pretty much any number that you've seen this year that we've talked about is considered a real number, okay? Like I said, you won't have to know the difference between real numbers and things that are not real numbers until you get into Algebra 2, okay? So like I said, up till this point and in this class, real numbers are just basically any number, okay? So to start off, if you're given any number, you should know automatically that it is a real number, okay? Now let's talk about how to tell what a rational number is. So rational numbers are any number that does what we call terminate, okay, or repeats when you put it in decimal form. Okay, so we use the word terminate here. So terminates or repeats. Okay, so the word terminate, the way you want to think of this word is this is just a fancy word for ends or stops. So if a number terminates, it stops. Okay. Now if a number repeats, that means it goes on forever. Okay. So the difference between these two terms here are terminate ends, repeat goes on forever. So you have something that repeats and goes on forever. So some examples of rational numbers are the number 2. Well, the number 2, it's just one number, so that means it actually terminates. It's not a number that goes on forever. There's not a ... at the end. There's no decimal or no number that repeats itself there. Okay? So in this case, this is a rational number. And just so everybody's clear, the reason this is a rational number is we can write it as a fraction as 2 over 1, or 4 over 2, or 6 over 3, or 8 over 4, or 18 over 9, or once again, there's a lot of different ways to write the number 2 as a fraction, okay? But this indicates to you that it is, in fact, a rational number, okay? Another example, we've got the square root of 4. Well, square root of 4, if we know what that is, this is the positive square root of 4. Well, that's just the number 2. So we already know 2 is a rational number. So the square root of 4 also has to be a rational number because it's nothing more than the number 2. Okay? What about negative square root of 4? Well, if we have the negative square root of 4, that number is negative 2. And even though the number is negative, it still terminates, okay? So that means we can write this as a fraction. Once again, negative 2 over 1, negative 4 over 2, 8 over negative 4, okay? So we can write it as a fraction or as a ratio. Let's see. So we also have 2.25, okay? 2.25 is a rational number because it's a decimal, okay, that stops. So notice it's not 2.25 and then 5555 or 2.25 and then a bunch of random numbers. And the thing is, it doesn't go on forever, okay? So this is a decimal, 2.25, and that's it. There's no more numbers out here, and it doesn't go on forever, so it actually terminates. So it is a rational number, okay? Negative 0.3 repeating, okay? This is actually a rational number because what this means is we have negative 0.3333 and so on and so on, okay? That's what this bar across the 3 means. That means it's repeating, okay? Well, this is a number that repeats when you put it in decimal form. So the decimal form is here. You can see the 3 repeats, okay? And this actually means it's a rational number. More importantly, this is the rational number negative 1/3. So it's the fraction negative 1/3, okay? So even if it does go on forever like this, if it repeats, it's still rational, okay? So you can't have rational numbers that go on forever, but they have to repeat. Okay, so some number or some sequence of numbers have to repeat. So another example of this is the number 0.05050505, and so on, okay? This number goes on forever, and you can see the numbers 0 and 5 repeat themselves over and over and over again, okay? So these are two examples of numbers that don't terminate, but they do repeat. So negative 0.3 repeating, or 0.505050, or 0.05050505, on and on and on and on. Okay. So all these are examples of rational numbers. So basically, once again, if it's a number that stops or terminates, or if it does go on forever, it has to repeat. But if either of those two things are true, it is a rational number. Okay, and we can talk later, and this is something you'll learn later on. We can go through. Well, technically, it's something you should probably already know, but we can go through and change each one of these numbers into a fraction if we wanted to. Okay, that's what the word rational means. Now, if we're looking at irrational numbers, okay, well, if rational numbers are numbers or any number that terminates or repeats when you put it in decimal form, irrational numbers are any number that doesn't terminate or repeat. When you put it in decimal form. Okay, so once again, keyword here is doesn't. All right, so if it doesn't do either of these things up here, it's what we would call an irrational number. And the most famous irrational number, go ahead and tell you, is the number pi. Okay, so if you actually go to your calculator, type in the number pi here, okay, then you'll see that the number pi is 3.141592654. Now, the one gripe that I do have with this calculator is this isn't truly what pi is. Pi actually continues on. So you see this last 4 out here, okay? It actually does not stop right there, okay? It actually goes on and on and on, okay? So technically what we have here with pi is it's 3.141592654, and then it actually goes on and on, okay? So it actually does not terminate. Well, that's the first thing. It doesn't terminate. But now we need to check, well, does it repeat? Well, since this decimal goes on forever, is there any number here that repeats over and over and over again, or any set of numbers? Well, no. 141592654. Okay, so there's no repeating pattern here. So since it goes on forever and there's no repeating pattern, this is what we would call an irrational number. Same thing goes with when you multiply any number times pi. So if you have the number 2 pi, okay, well, that's going to be 6.2831853007. And then it goes on and on and on and on, okay? So at the same time, this is a number that doesn't stop. It goes on forever. And notice it doesn't repeat. None of the numbers repeat, okay? So there's no set of numbers that repeat over and over and over again, no pattern, okay? So in this case, the number 2 pi is also irrational. Another number that is irrational is something like the square root of 2. So if you look at the square root of 2, once again, going back to the calculator, if you want to type in the square root of 2, you do square root of 2. And you see that they give you the number 1.414213562. But once again, this calculator doesn't do it justice, okay? So just to let you know, if you do the square root of 2, or you do the square root of any number that's not a perfect square, so same thing with the square root of 3, or the square root of 5, or the square root of 6, okay? You can see you get these long decimals out. And what this indicates to you is this actually does go on forever, and it doesn't repeat, okay? So when we go back to the notes, we have the square root of 2, positive square root of 2, I might add. So positive square root of 2, it's going to be the number 1.41421356 And once again, just by what I told you, that means it goes on forever, okay? You can notice here there's nothing that repeats over and over and over again. There's no pattern here, okay? So with that being said, the square root of 2 is also an irrational number. The negative square root of 7 is an irrational number, because once again, let's go to the calculator. Negative square root of 7. Well, we see that number is negative 26457511311. Okay, so if we go back to our notes, we see that negative square root of 7 is negative 2.6457511311. And once again, since this is the square root of something that is not a perfect square, so just to be everybody's on the same page, what I mean by perfect square, well, what if we took the square root of 4? Well, that's just the number 2. If we took the square root of 9, well, that's just the number 3. If we took the square root of 16, that's just the number 4. If we took the square root of 169, that's equal to 13, okay? So all these numbers here, the 4, 9, 16, 169, these are all what we call perfect squares. And if you take the square root and you get what we're going to call a whole number out, or an integer out, as we'll see when we define that term here in just a little bit, then these are rational numbers. If you take the square root of something like 7, okay, or the square root of 15, or the square root of 89, okay, or the square root of 125. Once again, notice every single one of these numbers, you get a long decimal out. And if you ever take a square root and you get a long decimal out like this, you're going to have to understand that this decimal actually goes on forever. So that means it makes these numbers irrational. So square root of 15, square root of 89, square root of 125. But we do the square root of 121. Well, that's just 11. That means that's a rational number, okay? So when we go in and we look at some of the examples and you do the practice, basically the calculator is going to be your friend, especially in terms of square roots. If you take the square root of a number like this and you get a big long decimal out, it's understood that number is going to be irrational, because that means it goes on forever and it doesn't repeat. So it doesn't terminate and it doesn't repeat. Okay. One more example of a irrational number is something like 0.1011011101110, and so on. Okay. So first off, these dots down here tell you that it doesn't terminate. So this decimal goes on forever. But then we look and see, well, it kind of looks like it's repeating, right? You see kind of a pattern here. But notice what's going on here. Well, is it the 1 that's repeating? Well, no, the very next number is a 0. Well, is it the 1 and 0 that's repeating? So 1, 0. Well, no, the next two numbers are 1 and 1. So it's not the 10 or the 1, 0 that's repeating. Is it the 1, 0, 1? Well, if you look, we have 1, 0, 1, 1, 0, 1. So it looks like 1, 0, 1's repeating. But then you look at the next three numbers, 1, 1, 0. Okay, that means it's not repeating. And you can actually keep going on, 1, 0, 1, 1. Well, the next 4 is 0, 1, 1, 1. So you can see here, even though this looks like it's repeating, so looks as if it is repeating, but it's actually not. So this is actually an irrational number, okay? Once again, it kind of looks like it kind of fakes you into believing that it's repeating because you see a pattern. And the pattern is between every zero, you actually add another one. So it's 1, 0. Well, there's 2 ones, 0, 3 ones, 0, 4 ones, 0, and so on. And like I said, that kind of looks like it's repeating because there's a pattern happening, but it's really not repeating. So this is actually an irrational number. This is a number we cannot write as a fraction, okay? So just to give you an example of that, because there will be some examples in the practice and there will be some on the homework, and also when you take the benchmark in the SOL where they'll try to trick you, okay? Where they'll try to make you think that, all right, this is repeating, but it's actually not. So you got to pay attention to your decimals and make sure it's truly repeating, okay? Once again, if it's not and it goes on forever, it is an irrational number. So let's go ahead. Now we need to talk about, so now we can see how to identify real numbers, rational numbers, and irrational numbers. Well, I'll go ahead and tell you, if you know the number is irrational, that's it. That's all we can say about that number. We can't go any further and call it any other type of number. It's just an irrational number. But if we have a rational number, so if we know it's a rational number, so what I'll write here is if you know the number is rational, you can actually check it to see if it's another type of number or another 3 types of numbers, okay? So if you know the number is rational, check the following. So what I mean by that is, well, first off, once again, we first have to know the number's rational. But if the number's rational, we can then check and see, well, is it an integer? Okay. So integers are a special type of rational number, okay? And the actual definition of an integer, okay, is that an integer is a number you can count to. So 5, you can count to 5, you can count to 10, you can count to 3, you can count to 1,000. You can actually count to 1,000,000 and 1,000,000,000 if you wanted to. Now, it'll take you a long time, but those are numbers you can count to, okay? So when I say numbers you can count to, it's something you can physically count to. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Like I said, even though it'd take you a while, you can count to 1,000,000, 1,000,000,000, 1,000,000,000,000, okay? 999,999. Once again, technically you can actually count to it. Once again, it doesn't take into account how long it would take you to count to that number. But if you can possibly count to the number, that's what I'm talking about here. So a number you can count to, it's the number 0 or the negatives of those numbers. So what I mean by that, okay, is numbers you can count to. Well, once again, I said we can count to 1, 2, 3, 4, 5, and so on and so on, okay? So ... here, meaning this goes on forever. So we can actually count to 1,000,000,000,000, okay? We can count to, not to confuse anybody here, we can count to 1,000,000,000,000, okay? Which is the next higher than 1,000,000,000,000, okay? Once again, even though these numbers are really big, it actually goes on forever. You can actually count to these numbers. It's basically numbers you can count to, okay? But I'll also say the integers they can be the number 0, okay? So an integer is, the number 0 is an integer, okay? And now I say the negatives of those numbers. So first off, there's not a negative of 0, okay? So the negative of 0 technically is just 0. So 0 doesn't have a negative, but what about the number 1? Well, what's the negative of a number 1? Well, that is just negative 1. Well, what's the negative of 2? Well, that's the number negative 2. What's the negative of 3? Well, that's negative 3. What's the negative of 4? Negative 4. And what's the negative of 5? Negative 5. And you actually can keep going in that direction and find the numbers of all negatives of all the numbers you can count to. So if you can count to 10, well, 10 would be an integer because it's a number you can count to, and negative 10 would be an integer because it's the negative of a number you can count to, okay? So one way to think about integers are, think of the number line, okay? What numbers are on a number line? Well, at the middle you got 0. To the right you got 1, 2, 3, 4, 5, 6, and so on, okay? So let me fix that 4. It looks a little wonky. Okay, so we have the positive numbers to the right, 1, 2, 3, 4, 5, 6. Well, we have the number 0, and then to the left we actually have the negative numbers. Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, and so on, okay? So you can actually go in the opposite direction and talk about the negative numbers, and those are actually also integers, okay? So one way to think about integers are they're the numbers that you see on the number line. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way as far as you can count. And then also the negatives of those numbers. So negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8, negative 9, all the way as far as you can go in the other direction, okay? So that's technically what an integer is, okay? Now, this is important because, as you've maybe noticed in the book, they classify some things as integers, and one of the examples we're going to do towards the end of the section relies on you knowing what integers are, okay? So you got to know what integers are. And integers, once again, are the numbers you can count to, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, on and on and on. The number 0 and the negatives of those numbers, okay? So basically any number you see here in either direction, and once again, don't forget the dots, okay? So anything bigger than 5, anything less than negative 5, that, once again, you can count to, those are what the integers are. Now, if you know that if your number's an integer, and we'll go through with this when we look at the examples, but then, so if you know your number is rational, then you know your number is an integer, then you can check and see if your number is what we call whole, okay? And the definition we're going to use, or the idea behind what a whole number is they are the numbers, so a whole number, so numbers you can count to and 0. Okay, so numbers you can count to and 0. Which, let me go back and fix one thing before I forget. So if we go back to integers, I say number you can count to. Well, it's numbers. They're more than one integer. So numbers you can count to, 0, and then I guess instead of or, we should say and the negative of those numbers. So all the numbers that you see listed here, these are called integers, okay? Well, if we look at this, whole numbers, these are the numbers you can count to and 0. So it's all of the integers there except the negatives. So we have 0, 1, 2, 3, 4, 5, 6, 7, and so on and so on, okay? So what you notice with the whole numbers is all these numbers are integers too, okay? The only difference is whole numbers cannot be negative, okay? So what I'm going to put in parentheses here is no negatives. So in this case, with whole numbers, you literally start at 0 and then you just count, okay? And if it's a number that you can count to, it is a whole number. Once again, 1,000, 1,000,000, 100, 127, 59,428, okay? Once again, if it's a number you can physically count to, then it is a whole number. Once again, the number 0 is also a whole number. And then once again, the difference between whole numbers and negatives or integers are, in the whole numbers, there are no negatives. So you don't have the negatives of these numbers here, okay? Now the last type of number, so if your number is rational and it's an integer and it's whole, then there's one last number that you can talk about that the number could be. And these are called the natural numbers, okay? So these are numbers you can count to. And that's it, okay? So the only difference between whole numbers and natural numbers is the natural numbers do not have zeros. So you actually start at 1, 2, 3, 4, 5, 6, 7, 8, and so on, okay? So natural numbers are just numbers you can count to. Now, to give you a little bit of a backstory on this, I don't want to take a lot of time in the video to describe this to you, but the reason we call these natural numbers is, well, when humans first started doing math, well, we actually didn't have the concept of 0. So I would have, so in the classroom here, we have 23 desks in the classroom, okay? I can count to the number 23, and I physically have 23 desks in my classroom. If I didn't have any desks in my classroom, well, when we started off with numbers, we wouldn't say we had 0 desks. We would just say we didn't have any desks, okay? Like I said, that might be a little confusing to some people to think through, but the reason we call them natural is naturally when you have things that you can count, like desks or apples or tiles on the floor or windows in a building, okay? You don't ever say you have 0. I mean, you can't physically have 0 windows in a building, okay? If a building doesn't have windows, we just say the building doesn't have windows. We don't say it has 0 windows, okay? Which now we do because we have the concept of 0. But if we're talking about 0, it's specifically a whole number and an integer and a rational number, but not natural. Okay, so once again, natural numbers are only the numbers you can count to. So the way this is different here is there's no 0. Okay, so you can kind of see as we go up, we add some things. So natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, yada, yada, yada. Well, whole numbers, it's all those same numbers and the number 0. Integers, it's all of those numbers we just talked about and the negative of those numbers. And then we go back and then we have every one of those numbers we just talked about is rational. And then every rational number that we talk about is real. Okay, so it kind of, if you know a number is natural, then you actually know everything else about it. You know that it's a whole number. You know it's an integer. You know it's rational, and you know it's real. Okay, and that's what we're going to get into when we look at the first example. Okay, so let's go ahead and look at example 1. So example 1. In this case, this has to do with classifying real numbers. Okay, and the instructions here say to classify each number. And what it means by that is we need to tell, so we're going to be given a number, and we need to tell what type of number it is, meaning, is it real? Is it rational or irrational? And then if it's rational, is it an integer? Is it a whole number or is it a natural number? So first up, we have the number square root of 12. Well, first step when we're doing any of these numbers, if the number's not already in decimal form or in standard form, we need to type this number out as a decimal or a whole number. Well, in this case, the square root of 12, well, look what happens. When we plug it into our calculator, we get a very long decimal. And once again, if you remember what I talked about with square roots, we take the square root of something that is not a perfect square, it's technically irrational because we have a decimal that goes on forever and doesn't repeat. Okay, so square root of 12 is actually 3.4641011615 ... Once again, goes on forever, so it doesn't terminate. And as you notice, there's nothing that repeats here. So there's no common pattern that goes through and no set of numbers that repeats. 464101615. Okay, so since the decimal does not repeat and it doesn't terminate, this number is irrational. But first things first, so this is the first thing. I need to backtrack here just a second. The very first thing we can tell about this number is the number is real. Okay? And that's going to be true for every number that you see here. The number is real. Now, after we know that the number is real, now we can go through, well, is it rational or is it irrational? And what we just talked about was this is a decimal that doesn't terminate, so it doesn't end or it doesn't repeat. Okay? Then this is what we would consider an irrational number. Okay? And that's actually it. The number square root of 12 is real and irrational, and that's it. Because once again, if the number is irrational, there's nothing more we can say about it. Now, if the number is rational, as you'll see in the next example, you can maybe say some more things about it. But if a number is irrational, that means it's real and irrational, and that's it. Okay? Once again, this is because this decimal does not terminate or repeat. So once again, that means it's irrational. Once again, any number is a real number. So as you'll see, every single one of these numbers we're going to talk about is a real number. The only thing that we got to determine is it rational or irrational? In this case, it is irrational, and that's it. That's all we can say about it. Part B, we have the number negative 0.25 repeating. So the 25 is repeating. I'm going to clean up that 0 a little bit. Okay, so if we actually write this out in true decimal form, this is the number negative 0.25252525, and on and on and on forever. Okay, so once again, that means the decimal does not terminate, but you can see what actually happens. Well, the 25 is actually repeating. Okay, so this is actually a decimal that does not terminate, but it repeats. So what we can say about that, well, first off, it is a real number. Okay, so right off the bat, once again, any number that you're going to see here, it's going to be real automatically. Okay, but then after that, we would say, well, is this number rational or irrational? Well, it doesn't terminate, but it does repeat. So what that means for us is that this is actually a rational number, which means we can write it as a fraction if we wanted to. Now, what that fraction is, at this point, we're not too concerned with it. Now, if you did want to know what this is as a fraction, we have ways we can go about turning this back into a fraction, okay? But like I said, that's not what we're worried about right now. We're worried about, can we write it as a fraction? Well, yes, we can, because it's a decimal. Even though it doesn't terminate, It repeats. Okay, so once again, this tells us that it is rational. And actually, that's all we can say about that, because then after it's rational, we could say, well, is this an integer? Well, if we go back and look at the integers, do the integers have any decimals in them? No. Okay, so since the integers don't have any decimal places in them, this is not an integer. So actually, we can stop right there and say this number is real and rational, and that's it. Okay? But now let's look at the case of what we'll have with part C. The negative square root of 9. So once again, the negative's out front of the square root. That means we're going to have this is the negative square root of 9. So this is going to be negative 3. Okay? So since that is the number negative 3, let's go through the list and see what it is. So first off, we automatically know this is real. Once again, every single number that we see this year, it is going to be real. Okay? So we go on to the next thing. Is it rational or irrational? Well, this number terminates, right? It actually doesn't have any decimal places. So this is just the number negative 3. So that means it is also rational. Okay, now this is actually an easy number to write as a fraction. It's just the number negative 3 over 1, or negative 6 over 2, or 9 over negative 3. Okay, all those fractions that I just sounded out, those are possible fractions for the number negative 3. So we know that this number is rational. Well, now we go and ask, well, is it an integer? Well, let's go back and look and see. Well, what is an integer? It is a number you can count to 0 and the negatives of those numbers. Well, since we can count to the number 3, and negative 3 is the negative of the number 3, and actually you see it right here in the list that I made, negative 3, the negative square root of 9 is actually also an integer. But then that's actually where we end up stopping, because now we would go and say, well, is it a whole number? Well, is it a whole number? Well, we got the negative 3. Once again, no negatives with the whole numbers, and the same thing with the natural numbers. So since this number is a negative, it is not whole and it's not natural. So that's it. The number is real, rational, and an integer. And that's it. Okay? So once again, think about how I'm thinking through this and how I'm going about checking each one of these, okay? So let's go on. There's still two more examples here. And I'm actually going to give you an extra example that's not in the book, so make sure you pay attention to that one. But let's go ahead and look at part D. Well, in this case, we have 72 over 4. Okay. So 72 over 4. Well, once again, right off the bat, we know it's real. So once again, even before we write the number out as a fraction or as a decimal, we know the number's real. Okay. Next thing, well, is it rational or irrational? Well, it's already a fraction. Okay. So 72 over 4, that's a fraction. So that's a dead giveaway that this is rational. But now we need to ask, is it an integer? Well, how we're going to figure that out is, well, what is 72 divided by 4? So if you need access and help with this, this is no problem. You can put this into the calculator. 72 divided by 4. We can see that that's just the number 18. Okay? So 72 divided by 4, that's just 18. Well, once again, 18 is real, 18 is rational. Is 18 an integer? Well, go back. An integer is a number you can count to. I can count to 18. So that means this number, 72 over 4, which is the number 18, is also an integer. Then we ask, well, is it a whole number? We'll go back to the notes. Whole numbers are numbers you can count to. I can count to 18, so 18 is also a whole number. And then the last thing we need to check, well, is it a natural number? Well, natural numbers are also numbers you can count to. So, in this case, it's actually also a natural number. So actually, this type of number, so the number 18 and the number 12 and the numbers 2 and the number 57, okay, those are actually all examples of numbers that are all real, rational, integer, whole, and natural, okay? The only thing that this number is not is irrational, and that's because a number can't be both rational and irrational just because of the definition. If a number is rational, then it can't be irrational because irrational means not rational, okay? So once again, it has to be one or the other on that end, but all the rest of these, it fits every other category, okay? Now, this is one that I've already talked about, but they wanted to give you an example of this as well. So part E, they talk about the number pi, and I already told you this is the most famous irrational number that there is. So we already know that this is irrational. But just to cover it again, this is equal to 3.141592654 ... Goes on forever. Okay, doesn't repeat. So once again, this is real. So every number, once again, is real. But then, since it's a decimal that goes on forever and doesn't repeat, this is also irrational. And once again, after we say it's irrational, we don't need to check that it's an integer or a whole number or a natural number because it's not going to be those. The only way it can be an integer, whole number, or natural number is if it is also rational. Okay? Now, this is the extra example I'm going to talk about. What about the number 0? Well, once again, it is a real number. Okay? It is, in fact, a rational number because it's a number that terminates. It's just the number 0. There's no other decimal places or nothing like that. It terminates. And actually, for example, the number 0 can be written as a fraction as 0/1 or 0/2 or 0/596. Okay? These are all representations of 0 as a fraction, so it is also rational. Well, then we ask, well, if it's rational, is it an integer? Well, let's go back and look at the integers, numbers you can count to. 0, okay, so 0 is actually an integer. And if it's an integer, we need to ask, well, is it whole? Let's go back to the whole numbers, numbers you can count to, and 0, okay? So 0 is actually a whole number. And lastly, we need to check, well, is it a natural number? Well, 0 is not a number you can count to. Once again, you can't count to 0, so in this case, it's not a natural number. Once again, this little note here, no zeros to the naturals. So this is only real, rational, integer, and whole. And I forgot to circle these, so I'll go ahead and do that. But this is how you go about classifying numbers. Okay? So, with that being said, let me go ahead and give you one other piece of advice here in terms of looking at classifying real numbers, and then we'll go and look at the last two examples on what you're going to have to do on those types of questions. But let me draw for you, and this is something you should probably write down and draw yourself. But let me go ahead and draw you the Venn diagram of the real numbers. Okay? So, first things first, Venn diagram. We're going to have this giant box. And this is all of the real numbers. So every number that you can think of as far as what goes on in this class. So pi, 72 over 4, 18, 0, square root of 2, negative square root of 12, square root of 12. All those numbers we've just talked about, they are all real numbers. That's what this box represents. All of the real numbers, any number you can think of. Okay? Well, after we know the number's a real number, we can either have the number be rational, or we can have the number be irrational. Okay. Now, once again, notice if you know how Venn diagrams work, notice there's no overlap between the rational and the irrational, but all of the rational numbers are inside the real numbers. So that means every rational number is a real number. Same with the irrational numbers. Every irrational number is in the real numbers. So no matter what your number is here, whether it's rational or irrational, it's going to be a real number. So once again, rational numbers are things like 1/2, negative 1/3, 2.25, and so on. Okay, so decimals that either terminate or repeat forever. Well, once again, irrational numbers. You have things like pi, 2 pi, square root of 2, negative square root of 3, 0.1211211121112. Okay. Square root of 12. Once again, you can think of more and more and more, but that's where all the irrational numbers are. And once again, if we know they're real and they're irrational, there's nothing else we can say about them. But the Venn diagram on the rational side, if we know they're rational, then we can actually break it down even further. So we can go and we can ask and see, well, are they integers? Well, the integers are -2, -1, 0, 1, 2, and going in either direction, okay? So if they're integers, that means if anything's an integer, it's also a rational number and it's also a real number, okay? Since all of the integers are inside the rational numbers. So you can kind of see if you have a number that's an integer, well, you can kind of work backwards. If it's an integer, well, then it's a rational number. If it's a rational number, it's a real number, okay? We can actually keep doing this because the next layer down are the whole numbers. Well, once again, that's 0, 1, 2, 3, ... Okay, going on forever. So once again, if a number is a whole number, well, then it's also an integer, and it's also a rational number, and it's also a real number, okay? And then lastly, the last little block here, these are the natural numbers. And once again, it starts off with 1, 2, 3, and then it goes on forever. So if a number's natural, it's also whole. It's also an integer. It's also rational, and it's also real. So in a way, it's kind of the way we've been doing it. We all know the numbers are real numbers. And then we check, is it rational or is it irrational? If it's irrational, that's all we can say about it. It's an irrational number. It's real and irrational. But if it's a rational number, then we can go and say, well, if it's rational, is it an integer? If it's an integer, is it a whole number? If it's a whole number, is it natural? Okay, so kind of think about it as kind of like steps down. Each time we're getting less and less numbers. Okay, but once again, all natural numbers are whole numbers. All whole numbers are integers. All integers are rational numbers, and all rational numbers and irrational numbers are real numbers. Okay, and like I said, as far as what's different than real numbers, okay, That's something you'll get into all the way. I don't think you'd see it until Algebra 2, okay? So this is all you have to worry about as far as this goes for this year and next year in algebra. But once again, make sure you copy down this Venn diagram, understand what this Venn diagram means, okay? They have a sample of it in the book as well, so you can see with the colors, they actually color code it, okay? But that's the thing. Make sure you understand what this Venn diagram means, because it might be a question that you'll see later on where you have to put a number in. So they might have you drag and drop. Well, this number, is it a natural number? Is it a whole number? Is it an integer, rational, irrational? What is it? Okay. So you got to know what the Venn diagram looks like. But with that being said, let's go ahead and go to the last two examples, okay? And this is where we actually get into the part of the question that where we need to approximate a square root. So the part of the section where it says approximating square roots, okay? So example 2. Once again, this is approximating a square root, okay? So what you're doing when you're approximating a square root is you're going to, and this is the type of question you'll be asked on this, is determine between which two integers, so there's one of the new terms being used here, between which two integers the square root lies. Okay, so there's actually a hard way and an easy way to do this. I'm going to show you the easy way. I'm going to talk about the hard way, but then I'm going to show you the easy way. So technically what you would do, so part A, we've got the square root, the positive square root of 71. Okay. Well, one way you can do this without using a calculator is you could think about the perfect squares. Okay. So if you think about the perfect squares, well, there's 1, there's 2, there's 4, there's 9, there's 16, 25, 36, 49, 64, 81, okay? And you can go through and list out all the perfect squares. Well, if you know 71 is between 64 and 81, well, then the square root of 71 has to be between the square root of 64 and the square root of 81, which is 8 and 9, okay? So the answer to this question is this number, the square root, is somewhere between 8 and 9. It's 8 point something, okay? That's approximating a square root. Now, the easy way for this, square root of 71, let's go to our calculator, okay? Square root of 71, we see that is actually an irrational number, 8.426149773, ... goes on forever. Well, all we have to do now is we need to know, well, this is 8.426149773, ... Once again, that's what we would consider an irrational number. But we can look at this number and we can actually tell, well, this number is 8.4. That means it's bigger than 8, okay? But it is less than 9. So if we look at a number line, think about where the numbers 8 and 9 are. If we had the number 8.4, yada, 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 that means we would be bigger than 8. So this number is bigger than 8, but it is less than 9. So the number's somewhere in between here. Okay, so the square root of 71 is between 8 and 9. And sometimes you'll see it written like this. 8 is less than, the square root of 71 is less than 9. And that's another way that you can write 71 is between 8 and 9. That means Square root of 71 is bigger than 8, but also less than 9. Okay? So sometimes you'll see it asked like this, and you'll have to give the answer like this. But other times, as you'll see in the practice, it'll just ask, between which two numbers is it? And it'll say 8 and 9, or 9 and 10, or 7 and 8, or -9 and -8. Okay? So just be careful. But once again, write the number as a decimal. The easy way is write the number as a decimal. And then once again, based on what you know about decimals, well, which number is this bigger than, and which next number is it smaller than? So now I don't think this one's in the book, but I'm giving you a part B. Okay. So once again, this is something that's not in the book, so make sure you pay attention to this. The negative square root of 27. Well, once again, the hard way about this would be like, well, okay, 27 is between 25 and 36. So the square root of 27 is between the square root of 25 and the square root of 26. So 5 and 6. But once again, we've got it negative. So technically, the negative square root of 27 is between -6 and -5. Now, once again, just thinking of it that way and going through it that way, which is perfectly fine if you see what I'm talking about there. That's one way you can approximate square roots. But once again, the easy way is go to your calculator. Negative square root of 27. You see that that's the decimal that you get, -5.196152423. Once again, dot, 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 because the square root of something other than a perfect square is going to give you a never-ending decimal that doesn't repeat, an irrational number. So we have negative square root of 27. Well, this is negative 5.196152.423 dot 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 dot. And once again, and this is why I want to give this example to you. Look at the number; it's negative. So if we look at the number line, we're actually going to be on the negative side of the number line. So we're actually going to be between the numbers -6 and -5. So think about it this way. -5.19. Well, you're going to count backwards. -1, -2, -3, -4, -5. And then there's a little bit more into the negatives. So you're going to be somewhere right here somewhere. Okay. And once again, that means the number is between these two numbers. So -6 and -5. Okay. So the simple answer here is negative square root of 27 is not equal to, is between -6 and -5. Okay. Once again, the fancy way, or the more mathematically accurate way, would be to say -6 is less than negative square root of 27, which is less than -5. So actually, the biggest number there is -5. -5 is bigger than -5.196152423, which is bigger than -6. Okay, so the two integers that negative square root of 27 is between is -6 and -5. Okay, so that's the first type of question you'll be asked about in terms of finding square roots or approximating square roots. So once again, easy way, do it in the calculator. But if you know what I'm talking about when I went over it the last time, all right, 71, it's between 64 and 81. So square root of 71 is between the square root of 64 and the square root of 81. So that's between 8 and 9. Once again, the logic is still the same. It's just we're taking the easy way out when we're talking about doing it with the calculator. Because once again, if you know what the decimal is, it should be clear between what two numbers that number is between. Okay? Now, last example, and this will be the last example for the section here. This is actually where we're getting into a very important topic here. So this is actually the first SOL that you're going to have to be able to do. In this case, it's about ordering real numbers. Okay. So in this case, ordering real numbers, this is where we need to compare. So we need to know which number's bigger, which number's smaller, which I've kind of been hinting at in class. And I've kind of mentioned in videos before, is that when we have all these different types of numbers, once again, we're going to be seeing, in this example, we're going to be seeing square roots. We're going to be seeing the number pi. We're going to be seeing a mixed number. So we need to know how to take all these different types of numbers and write them in the same way. And what I mean by that, well, let's go ahead and look at the example. So in this case, we're asked to order the square root of 5, pi, and 2 2/3, so a mixed number, 2 2/3, from least to greatest. Okay, so I want to point out this thing, least to greatest. That means we're going from the smallest number to the biggest number. So in your list, when you're ordering these numbers from least to greatest, you need to start off. Your list should start off with the smallest of these numbers, and it should end with the biggest of these numbers. And once again, it's in order. So it goes from the smallest to the largest in order. So how do we do this? Well, if we have all these different numbers, okay, the first step is going to be, let's write all these numbers as decimals. So go to the bottom here, and we're going to write, well, what the square root of 5 is as a decimal, what pi is as a decimal, and what 2 2/3 is as a decimal. So square root of 5, once again, we can use our handy-dandy calculator here. So square root of 5 is going to be square root of 5. 2.236067977. So once again, we take that number and we write it down. 2.236067977. And then ... It actually goes on forever. Luckily, we won't need all these decimal places, so this is fine, writing it like this. Okay, so that's the number square root of 5 as a decimal. Pi as a decimal. Well, we already know from the previous two examples we saw pi in. 3.141592654 ... Okay. Once again, if you need help knowing what pi is, go to the calculator. It has a pi button, and there is the number pi written as a decimal. But once again, it has the ... at the end because it's an irrational number, and it goes on forever. Okay. And lastly, we have the number 2 2/3. And if you haven't seen mixed numbers in a while, you could probably be a little rusty with this. But what we've technically got here is a mixed number is the number 2. So that's going to tell you what your ones place is. So it's the number 2. And now we need to know what the fraction 2/3 is as a decimal. And once again, if you don't know what that is off the top of your head, you can go over here. 2 2/3. Well, we know the 2 is in the ones place. Well, 2/3 is the fraction 2/3. That means the decimal places are going to be 6, 6, 6, 6, 6, 6, 6, 6. And notice out here it rounds it to a 7. But once again, this is another thing I don't like the calculator about, is it makes it seem like it's 0.666666667, but in reality it goes on forever. So how we actually write that is this is going to be 2.666666666. ... It goes on forever. But this is a rational number because the 6's repeat. So in this case, it's a decimal that goes on forever, but there's a certain number there that repeats, or set of numbers that repeat. In this case, it's the 6. So, well, how do we order these from least to greatest? Well, now that we have all these as decimals, we go through decimal place by decimal place and see which number's bigger and which number's smaller. So we want the smallest one first. Well, in this case, what is smaller, 2, 3, or 2? So it has to be either this number or this number. So it has to be the square root of 5 or 2 2/3. Well, since both of these are 2, we need to go to the next decimal place. And now we don't even have to worry about the pi. We know the pi is not the least number. So we go here to the next decimal place. We have a 2 and we have a 6. Well, which is less between the 2 and the 6? Well, it's the 2. So that actually tells us that in this case, square root of 5 is actually the smallest number. Okay, and notice when I write these numbers out, I don't use the decimal. Okay, I go through and I write the actual original number out. Okay, because once again, it's asking you to order these numbers, not these numbers. Okay, so we have square root of 5 is the smallest, so we can go ahead and put a star, or we can go ahead and put a check mark, or however we want to do it. We've already taken care of that number. Now we just have to look at these last two. Well, once again, which is the next least number? Well, which is lower, 3 or 2? So it has to be the 2 2/3. So the next number is the 2 2/3. And once again, that's because 3 is bigger than 2. We can tell right off the bat. And of course, when we get to the last number, that has to be the biggest number in this case. So pi is actually the biggest number. So this is the ordering of these three numbers from least to greatest. Now, if you so I'll go ahead and tell you the questions you're going to be asked on the homework and practice, and the questions you'll see on benchmarks and SOL, there's going to be more than three numbers here. Just to save us some time and just to get the gist of how this works, we just use the three numbers, okay? So what we end up doing here is, if we have more than just three numbers, we would just go and write out the rest of the numbers here. And it works the exact same way. We check it decimal place by decimal place until we get a number that's bigger or a number that's smaller. Now, I do have to say, be wary, okay? You could also be asked to order from greatest to least. Well, if least to greatest means smallest to biggest, well, then greatest to least means that it's going to be biggest to smallest. So it would be the exact opposite. You would want to list the biggest number first. So in this case, from greatest to least, it would be pi, then 2 2/3, then square root of 5. So basically your list just flips around. So if you do accidentally work one of these out and you do it from least to greatest, but then you were supposed to do it from greatest to least, one hint for you is you can actually just flip the list around, read it from backwards, and that's actually your list in order from greatest to least. Okay? So once again, do pay attention to that and make sure you're paying attention to what you're being asked to do. Is it least to greatest? Is it greatest to least? Okay? Make sure you pay attention, but the process is always the same. Label your numbers out as decimals, so lay your numbers out as decimals, and look at each decimal place and see which number's bigger and which number's smaller, okay? And like I said, you'll be practicing with this, with the practice and the homework, so if you do have any questions on this type of question, please let me know. But like I said, there's only, I think, like 3 on each of the practice and the homework like this. But like I said, it takes a little bit of time, but write each number out as a decimal and then check which number is bigger and which number is smaller. Now, on top of that, make sure to pay attention to any negatives and know how to deal with negative numbers, telling which one's bigger, which one's smaller. Okay? Pay attention to negatives. So if you have negative numbers, and I think I've given you at least one, 2, or 3 of those. I think 3 of those on the practice and the homework, okay? So with that being said, make sure you know how to tell which negative number is bigger, which negative number is smaller, okay? Now, if you do have issues with that, that's something we can correct later on. But like I said, pay attention to the negatives, and make sure you're paying attention which order you got to do it, from least to greatest or greatest to least. Okay. But other than that, that's the whole section here. So section 7-3 or 7.3, okay, approximating square roots, and then also classifying numbers. And like I said, even at the end there, we got a taste of ordering real numbers and seeing what the whole deal is with all these different numbers, okay, which one's bigger, which one's smaller. Like I said, we're going to be practicing that example 3 question types like that a lot here in the next little bit, okay, especially after we get through with percentages, because that's another type of number we can add into these are percentages, okay. So you might have a number written as a percentage. Well, you need to know how to write the percentage as a decimal in order to see which one's bigger and which one's smaller. But other than that, make sure you go through, watch the video, or you've already watched the video if you've gotten this far. But make sure you review the notes, and you can use your notes in this video when you're doing the practice and the homework. Just make sure you're taking your time and really, making sure you're doing these questions correctly. And like I said, if there's any question at all, you don't know what you're doing, you got a question wrong on the practice and you're not sure why, make sure you get those questions answered before you attempt the homework, because the homework grade is for real, okay? It's based on whether you get the question right or wrong. So use the practice to make sure you understand how to do each type of question before you go on to the homework, okay? But once again, any question at all, let me know. But other than that, thank you for watching, and good luck on your practice and homework.